Hello, and thank you very much for inviting me here. It is a real pleasure to be here at the, of course, here at Cambridge, but also at the Center for Life in the Universe. And I will show you that we basically built something very similar at Cornell University. So today, because we only have 20 minutes and this is a review, it's gonna be a bit of a road trip through everything you've learned and what we want to do now. And please feel free to find me at the coffee break to ask any questions. I've tried to put the most interesting things together, lots of questions to be asked. So it's characterizing these rocky planets, but what it allows us now to do is starting to characterize potentially habitable planets. And this is, in my view, the end goal for me. I think it's amazing that we have a lot of really interesting Jupiters and mini Neptunes, but I'd be really curious to know if there are other habitable worlds out there. And so to just break your perception of what we're looking for, I'm giving you my artist impression of the Earth, just colored wrongly and flipped by about 90 degrees so it doesn't look exactly like our planet. So if you can imagine, this could be a habitable world somewhere else, but with different kind of biota dominating. And we'll get to why for different stars, that's actually very high probability that it should be green. But first, I wanted to say hi from the other center that is trying to find life in the universe at Cornell. So this is the Carl Sagan Institute. We're about 40 faculty. I founded it in 2015, and there's a lot of postdocs and grad students, and we have 15 departments currently working together, trying to figure out how we can find life in the universe like you do here. So it's beautiful that it is mirrored from both sides. And so come visit. You're probably going to find somebody in all different departments that are happy to talk to you. So another thing, because I'm not going to have enough time today, I wrote a review in 2017 about how to characterize potentially habitable worlds. There has been a lot of things going on since 2017, but not specifically in this topic because we don't have the data yet. So it's pretty up to date, and I was trying to write it so that it is encompassing what we want to do. And in case you don't want to read a review paper, ta-da! I just published public science books on this topics. Alien Earth just came out in April, just in case it's a little bit of a lighter reading with lots of cool stories about how this field got started as well. But let's get to the challenge. The challenge is not just to find a planet at the right distance, right size, right energy input. It's actually to identify whether or not this could be a habitat. And here the context is critical. A lot of things, one of the things I would like you to take away is that just things that indicate life on the Earth do not have to indicate life on a planet that's very, very different. The further the planet is different from our rocky planet with a temperate water, ocean, and temperate temperature, the more difficult it is to interpret what we see. And so just keep that in mind whenever we're now exploring this fascinating diversity of exoplanets. Because one of the first things that we found is that there's a huge diversity. And Jane has talked about this before already, but basically there is this region where we have most of the planets we found between Earth and Neptune. We don't have a mini Neptune or a super Earth in our own solar system, but the most abundant planets that we can find, and Sasha was telling you about the problem of this is not complete because it becomes harder and harder to find long period planets. But the most abundant ones, and so this is from my review 2017, but then Sam Quinn from CFA just updated this. So this is an updated view of the planets we have. The most common planets are planets we don't have in our solar system. What is exciting, because there's a lot of different kind of environments that might potentially also be interesting habitats. I should say very quickly about the color coding. Here you have the host star as the color coding, and you see the smaller the planets get on average, the smaller the host star, because it's easier to find small stars around small host stars, right? The contrast is better. And so when you look at it differently, when you look at mass versus radius, now you start to see patterns emerge. And I think this is the critical step that we have made in exoplanets. We now have more than 5,600 planets, and thus we can start to see patterns that indicate formation or evolution of these worlds. What you see here is two blobs, basically. These are the hot Jupiters. Here you see the mass and Earth's masses and the radius and Earth's radii. And I also gave you the error bars on these measurements. Never forget that we have error bars. So some of these things are very, it's just good to know that the measurements always have error bars when you're trying to interpret what you see. So if I zoom in on the rocky planets that I want to talk about today, then this is a zoom in to about 10 Earth masses. It's 40 here, and then about 5 Earth radii. You still see a huge diversity of worlds. Now there are lines in this plot. These lines are mean density lines. What that basically means, if a planet is made out of rocks like the Earth, same composition, then it should lie on this green line here. If it has 50% of water, then it's this turquoise line up here. And the 100% water line here is just there to draw your eyes to show you anything above that line has to have a huge amount of gas. We do not expect the planet to be just pure water ice, right? But it's a good line just as a first approximation that everything above this is a mini Neptune. And so when you look at it, you see a big diversity. And now I've color-coded it differently. I color-coded it with the flux that the planet receives. Because with more and more planets, you're starting to see patterns because of the environment that it is in, right? So red is really hot and intense irradiation, and blue is coolish. And please, if you use this, please use irradiation of a planet if you talk about rocky worlds, because the equilibrium temperature you get makes no sense. Venus and Earth, if you just do equilibrium temperature, are pretty similar, so it doesn't tell you much. But the incident irradiation, right, if you don't know the albedo of that planet, that tells you if it's more in a category of a Venus, really hotly irradiated planet, or an Earth kind of temperate irradiated planet. So here you see the incident flux. This would be equilibrium temperature that you get, so you can translate it, but please use the incident flux if at all possible, because it makes much more sense. It tells you about the environment the planet is in. And the equilibrium temperature is not a temperature anywhere on the planet. Doesn't have to be its surface temperature, doesn't have to be anywhere in its atmosphere. An equilibrium temperature is not meant to give you the characteristics of a planet. So when we look at these rocky worlds, you have really hot ones, or some that are irradiated strongly. And we're starting to get to some that are within the habitable zone. And then we're starting, just really starting, to probe the outer edge of the habitable zone as well. So to put these puzzles together, you look at planets at different distances, orbital distances of the host stars. And so from lava worlds to potential habitats, because we know of planets that go in about 18 hours around their host star. So every rock that I know, every mineral that I know would actually melt. So we have lava worlds that we already spectroscopically addressing with JWST, and as Jane was just saying, also we're going to do this with the high resolution observations. What is amazing, because it's going to give us characterization of what these rocky lava worlds are made of. And that should give you some insight about what's going on in the interior, what's going to be outgassed, how it formed. And that's, of course, the first talk that we heard today. But the measurements we have is the star, a certain distance, and then you have a planet. And then if you want liquid water on the surface of a planet, the so-called habitable zone, you get to about plus minus 70% of what the Earth gets right now in terms of flux. This is, of course, depending on the atmosphere, but it's an empirical habitable zone limit if you want to use one. And then there's another zone that kind of at one point overlaps. It's a Venus zone if it gets hotter, and we do not understand where their overlap starts, right? What irradiation does a rocky planet get to become a Venus? We have models for the evolution of Venus. We have models of the future evolution of the Earth, but we do not know at what irradiation that actually will happen. And then if you're really, really close, lava worlds. Those are the ones we already probing. And then the question is, of course, there's probably something between the lava worlds and the Venus worlds, but nobody has come up with a name. So if you fancy yourself being forever in the astronomy literature, come up with a name. We don't have anything between lava worlds and Venus worlds yet. But just to first order approximation, we have a huge parameter space. So what we do is we explore it mostly in a 1D setting. Of course, you can do this in 3D too, but you don't have the resources generally to do this for thousands and thousands of planets with different compositions, with different irradiations, with different histories. And I love Jane's phrasing of a 4D environment. So you have to do the history, the dynamics, and what's going on. So I strongly believe that the 1D exploration is actually a strong tool where we can probe the physics of what should happen under different conditions. And so what you see here just is how complicated a rocky planet is if you're used to working with stars, if you're used to working even with hot Jupiters. Here you have surfaces that can actually reflect like clouds, they can absorb, there's latent heat, there's photochemistry in the atmosphere. So this is why I'm saying we understand this pretty well for the Earth. And if this was an Earth atmospheric conference, that everybody would say no, right? Because they're actually like parts per millions, but we have an understanding for the Earth. But the more different the environment gets, the harder it is to interpret what you see from the 1 pixel that Jane was talking about. And then, of course, the incident irradiation, the flux you get hitting this planet, has a different distribution depending on what host star you're talking about. And I said that most of the planets are around red stars because there we can actually find small Earth-sized planets within the habitable zone. They don't need as much time to go around their star because they have to be closer, and they provide a bigger signal. Even for direct imaging, they have a better contrast ratio. For transits, they have a better ratio star to planet. But if you look at the spectrum of a red star, and I'm sure you're familiar with this, it actually starts to deviate quite a bit from a black body. So do not use a black body, please. We have a lot of papers in the literature that use black bodies for M stars and then decide what the planet should look like. Please don't do that. Use the real M star spectra. However, there's a lot of discussion about the UV part here, because for a lot of active young M stars, we don't have a good UV part of the spectrum. So we're working with approximations, we're working with specific examples that we then extrapolate for other planets. And I'm not going to talk about this because there's going to be an hour from here. I'm still going to be here and tell you about all these fascinating intrinsic things about the interior of planets and how the outgassing will change the atmosphere, how the composition, and so Anders was talking about this initially, how this magma ocean and what it actually captures, how that will influence the primordial atmosphere. And then when we're talking about atmospheric escape, again, find me in coffee breaks. I could talk about this. I love this stuff. I have a whole institute with the different aspects, so talk to me about it. There's lots of interesting stuff to do. But, and especially if you're interested in lava worlds, for example, there's a really interesting review, Chow et al. 2022, about what they could be like. Fascinating things that we're starting to probe now. So I said that the incident irradiation is critical, right? To figure out what these planets should be like, first order approximation. So you can already take all the known exoplanets and figure out where that line is. And remember, red flux of the star, this is the stellar temperature, is different than blue flux. So that line is not straight, it's a little bit tilted. But basically you can figure out which planets are in the lava world category. And this is work that we started to pioneer with Yamila Miguel. She was a postdoc with me in Heidelberg. In 2011, we basically used this concept of what a lava world is and applied it for the first time to known exoplanets. That, at that point, we only had Kepler exoplanets. We didn't have that many, so this is way better. This is from one of her students right now. But you see that we have a lot of choices of really interesting planets to probe to see what they're made out of. And so this is Jonas Björn. He's a person in my lab. Because the big problem we have is now we have these lava worlds, but a completely different composition of minerals. How would the lava actually look like to my telescope? So we started to melt our own planet. We have a lava world lab, and Jonas, for example, is a geologist who actually works with lava. And so we are melting our own tiny lava worlds. Feel free to talk to me about how tricky this is and how many things can go wrong. But we want to and need a database that actually compares now this JWST observations or the ELT observations, or VLT for now, because a basalt at room temperature looks nothing like a basalt at 2000 degrees. Trust me, I've seen it. But it makes sense, right? Lava looks different from its counterpart at room temperature, and there is no database that actually has that information. So we are building one right now. And there's a couple of really interesting cases I want to draw your attention to. Planets very close. So at the edge, remember I said Venus and Earth, and we really don't know where the difference or where the change starts. And so there's, for example, LP899 that is at this inner edge. And so Rebecca Bainey, one of the postdocs in my team, has made the models. And so depending on what stage that planet it is it a hot Earth? Is it already in the runaway greenhouse state, or is it already a Venus? Actually, the atmosphere will look different, and this is a simulation of what JWST would see if it looks at it. And this is done by one of my undergrads who's now at Caltech. And so you can do a lot of probing of these planets if you pick them specifically and if you ask very specific questions, because where does the change appear? But let me get back to the point of now we want to do life, or at least science for habitability. So the statistic is that 1 in 5 stars has a planet at the right distance and small enough to be a rock like the Earth. 1 out of 5, 200 billion planets in our galaxy alone. Lots of opportunities to observe, but incredibly hard to do. But what can you actually search for? And so when you look, I think one of the key things is try to be as wavelength agnostic as you can be, because each part of the wavelength range actually gives you information. And I know this is a lot to look at, but it's just to say that if you're in the visible to infrared, you have features. This is in transmission. This is in emission or reflected light for the visible to infrared. And then this is an emission. But what it just shows you that there are features you can look for. And on the Earth, and this was the first science paper I ever wrote, for about 2 billion years, the combination of oxygen with methane, or ozone with methane, gives you an indication that there's life on this planet. So that's, in a way, a golden fingerprint you want to look for. And so Jane and her team have tried to figure out how we could do this with the ELTs, and we're trying to do this also with JWST right now. Of course, it changes because through geological time that changed. But there are databases, high resolution and lower resolution, that we made that are available for anyone who wants to try this. And so this is just a feeling of how it would change, so it guides your eyes a little bit. So this is the spectral evolution in the reflected light. Of course, oxygen, when you go back in time, disappears. Methane feature becomes stronger. This is the same in transmission spectroscopy. So again, different kinds, it will actually allow you to get more information on your planet. The opportunities are the small stars because they give you an amazing contrast. And so this, for example, is for the TRAPPIST-1e system and what JWST could see. But you might want to have a different line of evidence. And this is now where we step far into the future, where we have a telescope, as Sasha was saying, that can identify or directly image rocky planets. And so a second line of evidence, in addition to gases in the atmosphere, is actually biopigments. But there was no catalog of biopigments available, so we made one. And so this is one of my postdoc, Licia Coelho, who is a microbiologist. And so we have characterized the biopigments, the reflection spectra, for about 300 biopigments. Some of them that could strive in ice, and so she's a 51 Peg Fellow right now that also links us to the icy moons in our system. And you might have seen this. Purple might be the new green, because there are some biota that can actually strive in red light. It's biota that actually lives on the Earth too. And it might have been that the Earth was purple at one point too, before photosynthesis evolved, once the Earth was actually shielded from harsh UV radiation. One last point I'm not going to go into is there is fast initial characterization if you want it. It's using machine learning, so we have a couple of papers on that, just follow the water. It's actually machine learning. If it knows what patterns it looks for, it can identify water on rocky planets much better than I thought it was doable. Again, hard, but you could actually do it even for smaller telescopes. Signal to noise of about 20 is required. Happy to talk. This is one of my undergrads who's now at University of Toronto who did that work. So what I wanted to give you is a new view of how we can start to understand a slew of rocky planets, because that context is going to be critical for us to understand what we're seeing with the James Webb Space Telescope, with the ELT observations coming up, and how we want to design the Habitable World Observer or the LIFE mission here in the European side. But the future is bright. It might be purple, but with everything that we're doing right now, it's the idea of going even a step further, of using the information we have, specifically the small amount of times we get on JWST, to ask the right questions, to get as much information as we can about rocky planets and how they work in the whole run. With that, thank you very much.